Today we'll start our study of aerodynamics by looking at a few fundamental concepts from fluid mechanics. Aerodynamics is the study of how fluids move around an object. Now you'll notice I said fluids. We need to define what fluids means in a little more detail. A fluid is a substance that deforms continuously under the action of a shear stress. So what do I mean by that? If I look at this ruler, if I apply a load to this ruler, it'll deform. So if I put a fixed load on there, it deforms a fixed amount. Let's see if you can see that. But it doesn't continuous mean it would just keep on flowing. So a fluid, when you apply a shear stress to it, it just keeps on deforming continuously for as long as the shear stress is applied. It can be a gas or a liquid. We're familiar with both gases and liquids. The basic difference, if I pour a liquid into a container like a cup, the liquid will take on the shape of the cup, but the volume of the liquid stays fixed. And what I'll see is there's an interface between the liquid, the top surface of the liquid, and whatever gas is above that liquid. We call this interface a free surface. Now let's look at a gas. If I pour gas into that same cup, I'll see some different behavior. The gas is going to expand to fill the entire cup. In fact, it's going to spill over. It'll fill the entire room unless I put a lid on the cup. So the gas fills the space, but the volume is not fixed. It will expand to fill the entire space. We'll also find that there's no free surface with the gas. Now, if you look at that, you could look at the intermolecular forces. With a liquid, the intermolecular forces are pretty strong. I'll put liquid here. If I compare the liquid to a solid, the solid has very, very strong intermolecular forces. The gas has weak intermolecular forces. So with the liquid, we allow motion between the molecules, but they tend to stay close to each other. With the gas, we have motion between the molecules, but they can be very far apart. Next, I want to introduce the concept of a continuum. And by continuum, I mean, do we have to pay attention to all the little individual molecules? Or can we treat this substance, the liquid or the gas, as if it's continuous? So I don't actually see the individual molecules, I just see a continuous distribution of properties. So let me switch pages here. We call this the continuum assumption. So when is this continuum assumption valid? Let's just think about it physically for a moment. If I'm at sea level, I don't feel individual air molecules striking me. I know that they're bouncing off of my body, but I don't feel that. I just feel a continuous pressure. I don't feel any time variations in that pressure. But if I were an astronaut in outer space, there are air molecules in outer space. They're simply very few and far between. So if an air molecule happened to hit me and I had a force scale that could measure that, I would see there would be no force, and then there'd be a little spike. Boom, there's a force, and then no force, and then another little spike whenever an air molecule hits me. And so pressure as a function of time in outer space is going to be this sort of discontinuous function. It's going to have little spikes of pressure with zero most of the time. And so in outer space, way outside of our atmosphere, the continuum assumption breaks down. And there's got to be some sort of range in between. To answer the question of when this is valid, we need to think about length scales. So in the length scale of interest, L, we'll call it capital L. Is much larger than the mean free path of motion between molecular collisions. That's when this is valid. We'll use the symbol lambda to denote the mean free path. And it's the ratio of these two. So we're going to look at the ratio mean free path divided by the length scale of interest. And that's given a name. It's called the Knudsen number. Now, let's give an example just to illustrate this. If we have an airplane, the wing is really the aerodynamic lifting surface. The mean free path we might take as, we could take it as the wingspan or maybe the chord. So let's say it's the chord of an airplane. And let's say an airplane has a chord of 1 meter, so roughly 3 feet. If you remember, the chord is the distance between the leading edge and the trailing edge of the airfoil section. So let's evaluate the Knudsen number at sea level and the Knudsen number at an altitude of, say, 100 kilometers. There are ways to estimate the mean free path. I just went and looked it up on the internet. At sea level, the mean free path for air molecules, that's mainly oxygen and nitrogen, is approximately 8 times 10 to the minus 8 meters. Or that's approximately 10 to the minus 7. Now let's look at this high altitude of 100 kilometers. The mean free path at 100 kilometers is about 0.16 times 10 to the minus 2 meters. And I'll divide that by my chord, or length scale of 1 meter. And so I see that's about equal to 10 to the minus 1. So I see a big difference in these two. At sea level, the continuum assumption is pretty valid. In fact, for any Knudsen number below about 0.01, the continuum assumption is valid. And these are actually the conditions where most vehicles that we're interested in live. So for example, aircraft, submarines, maybe automobiles, trains, or it could even be spacecraft while they're traveling in the atmosphere. Now you might ask yourself, well, why is this continuing assumption? Why is that even important? Why do we even worry about this? The reason we worry about it is that when we look at fluid properties, if the continuum assumption is valid, then our properties are essentially time invariant. We don't have to worry about the mechanics of individual molecules. We can use time average properties. If my continuum assumption is not valid, then I'm going to have to actually worry about molecular collisions. That's a much harder computation. There's actually some regimes called slip flow or transitional flow. So as aircraft are very high in the atmosphere, fluid mechanics is a bit different. If we get out into sort of outer space, it's what we would call free molecular flow. And that's beyond the scope of this course. So let's look a little more at fluid properties. So we said we're going to assume a continuum. And the nice thing is that our fluid properties now can be time averaged over a large number of molecular collisions. And but what are these fluid properties we're talking about? Let's list a few of them. So I'm going to make a table with one heading being properties. Then I'll list the symbol we use. And it's also important to remember units. First, let's say temperature. So the symbol for temperature is T, and the units are degrees Kelvin, degrees C, Rankine, Fahrenheit. Our next property that we're going to look at a lot in this course is pressure. Pressure has a symbol of P, and typical SI unit would be pascals, which is a Newton per meter squared. In English units, oftentimes you'll see PSI, which is a pound per square inch. Sometimes you'll see PSF, pound per square foot. Density is the next property we're interested in. We generally use a symbol of rho, and typical units would be kilograms per meter cubed or slugs per foot cubed. Now I mentioned in the introduction of the course that we're going to ignore viscous effects, at least for the bulk of the course. The last couple of weeks we're going to talk about boundary layers. When we start talking about boundary layers, we're going to introduce viscosity. Viscosity is actually, we call it a coefficient. It's a relationship between the applied shear stress and the strain field. So viscosity coefficient, we typically use a symbol mu. And units for viscosity would be kilograms per second meter. Sometimes you'll see a different viscosity coefficient thrown out there. It'll look like this, nu, which is defined as the viscosity divided by the density. We call this the kinematic viscosity. In addition to properties, we also have relationships between properties. And you saw this in your chemistry class or your thermodynamics class. One of the real common, we call this an equation of state. One of the real common ones is the ideal gas law. Let me introduce that with an example. Times a specific gas constant R times T. So it's a relationship between pressure, density, and temperature. The pressure and the temperature must be in absolute units. R I mentioned it's the specific gas constant. There is a universal gas constant. To get R, you divide the universal gas constant by the molecular weight of the gas. So let's consider air. Let's say it's at 20 kilopascals, a temperature of 280 Kelvin. And what I'd like to find, so that's what's given, air at 20 kilopascals and 280 Kelvin. I'd like to find the density. So let's see, I'm just going to use my ideal gas law. I'll just rewrite this as rho is equal to P divided by RT. So to be able to sub into this, let's see, I've got the pressure already. Let me just write it in here. Pressure is 20 kilopascals. Temperature was 280 Kelvin. My gas constant for air, and you can look this up, but you should get to where you remember it. R for air is 287 meters squared per second squared Kelvin. So I'll just divide by the gas constant, 287 meters squared per second squared Kelvin. And I see that my units don't cancel out. Let me change my color of my pen here. The kelvins cancel, that's nice. But I've got kilopascals and meters and seconds, so I've got to massage my units a little bit. A kilopascal is 1,000 newtons per meter squared. And a newton is a kilogram. So 1 newton is equal to a kilogram meter per second squared. Now let's see if I can get things to cancel out. I see the second squared cancel. My kilopascals cancel. I got my newtons to cancel. Let's see, I've got meters to the fourth on the bottom and meters on the top, so one of these cancels. Now I've got, what I'm left with is kilograms per meter cubed. And that's the correct units for density. When you run the numbers, you'll get something close to 0.25 kilograms per cubic meter. And a few things I want to point out. If I were to write this down as 0.25 and forget the units, it would be wrong. Absolutely 100% totally wrong. Because 0.25 is not the same thing as 0.25 kilograms per cubic meters. Here's a little example. So if I say the pressure, don't write this down, but if I say the pressure is equal to 20 kilograms per meter squared. If I were to say that to you, you would think I was an idiot. I mean, pressure is force per unit area. What I wrote there is mass per unit area. There's no way in the world that can be right. And yet I'll tell you, there's seniors that are graduating this semester, then their senior reports have written things like that because I've seen it. Don't let that happen to you. Be very, very, very careful with units. Next thing is be careful with your numbers. So I'm going to take a moment here and pull out my calculator and check this number. Yep, so I just ran the numbers again. I got 0.24888, so I rounded it up to 0.25. All right, so a few things I wanted to illustrate here, just sort of general problem solving. When you're solving a problem, be sure to write down what you're given, write down what it is you're asked to find, write out your solution, your whatever equations you're going to use, your approach. Last thing you should do at the very, very end is sub in numbers. And whenever you sub in numbers, also substitute in the units. And then cancel out your units and make sure they all cancel. In that short example on the ideal gas law, we had to do a few unit conversions. And yeah, they were simple. They were in the SI system. But it's worth looking at units in a little more detail. What I have here is a table that I illustrate the systems of units. And I wanted to talk about how systems of units are created. Let's look at the SI system first, because that's the one we're the most familiar with. In my table, the left-hand column, I'm going to list the system. So this would be SI, which stands for System International. The next four columns are the basic dimensions. Now, a dimension is a physical quantity, like the length of something, or the force that's applied, or the mass that an object has. And a unit must be assigned to a basic dimension. In SI, we take kilogram to be the unit that is used for mass. Meter is used for length, and seconds are used for time. And then we have a derived unit. I'll write it in red. In SI, the derived unit is a Newton. And this simply comes from Newton's second law, F equals ma. So a Newton is defined as, I'll just write it up here, a Newton is defined as a kilogram meter per second squared. Or I can divide through by the kilogram meter per second squared, and I get a conversion factor. 1 is equal to a Newton second squared per kilogram meter. And in that previous example, I used that conversion factor to help clean up my units. Now you'll notice that force here, force in this system of units is not a basic defined unit. The force, the unit of force, is the derived unit. Now let's look at one of the English systems. It turns out there are several English systems. In the British gravitational system, our basic defined units, let's see, for mass, well, what if we use mass as our derived unit? So we'll define our unit of length as a foot, our time unit as seconds, and let's define force as one of our basic dimensions. And the unit we're going to use is called a pound. And I'm going to put an F subscript on it just to emphasize that that's a pound force. And then our derived unit would be a slug. And if I look at F equals ma again, let me just write it down here at the bottom, F equals ma. If I want to derive my unit of mass, then the mass is going to be F over A, or a slug would be equal to a pound force divided by a foot times a second squared. My conversion factor then is going to be 1 is equal to a pound force second squared divided by a slug foot. And that's used exactly the same way as we have in the SI system. So this is sort of a direct analogy to SI, but the only difference is our derived unit now is the unit associated with mass. Now here's the kicker. There is another English system that is common in engineering practice, especially in the US, and you need to become familiar with it. Let me lay it out for you. The English engineering system. For the English engineering system, we will take our unit associated with mass as a pound mass. Then for length, we'll use feet. For time, we will use second. And here's what's weird about the English engineering system. It's overprescribed. We go ahead and define a pound force to be our unit for force. So we've overspecified. We don't really have a derived unit. And what this does is it changes our conversion factor. Our conversion factor now has to have another quantity in it that depends on the acceleration of gravity. Our conversion factor is now 1 is equal to a pound force second squared divided by 32.174 pound mass foot. And that's kind of unusual. The way I remember it, that's not always the easiest way to remember things. Again, I go back to Newton's second law, F equals ma, and I just plug in what I have. So F is going to be my pound force. My mass is going to be my pound mass. I'll put it over here. I'm going to leave a little space. And then my acceleration, I'm going to plug in the acceleration of gravity. 32.174 feet per second squared. So that's the way I remember that conversion factor. Sometimes you will see people define this conversion factor, they'll call it G sub C. And if you look at older engineering textbooks, they would actually write the G sub C into the equations. I think that's kind of silly, it's just a unit conversion factor. It's numerically equal to 1, we see, and I can multiply and define anything by 1, and I haven't actually changed it. All I've done is a unit conversion. So it's important to remember this stuff. I thought it was worth the time just to go through systems and units in detail. We'll move on now. What we're going to do in the next module is look at systems and units in a little more detail, and it turns out we can play some games with this, what's called dimensional analysis. You may have seen this before. If you took fluid mechanics, you spent a lot of time with it. If you took the intro to Aero, hopefully you spent a little bit of time with it. But we'll go through dimensional analysis, and we'll start to understand where these non-dimensional numbers. I threw out the Knudsen number. That's a non-dimensional number, Reynolds number, Mach number. You've heard of some of these. And we'll figure out where do these things come from. That's it for today.